So, okay, let me share. Do you see my screen?
Yes, we see the screen.
Okay, so I'm happy to go whenever it's good.
Okay.
Okay, let me share. Do you see my screen?
Yeah, so live is okay. Yeah. So, hi everyone. Thanks for joining. Without any further ado, I just want to give the control to our guest that accepted our invitation for today's presentation. Alexander, Pierre, and Igor from Meta AI, who are working on very cool and important privacy preserving tools for machine learning. Please go ahead, Alex.
Thanks, Mohammed, for the introduction and for the invitation. So today we're going to talk about privacy attacks and DPSGD. And especially we're going to talk about our two open source frameworks that we develop at Meta. So privacy attacks is through the privacy linter, and our implementation of DPSGD is in Opacus. So I will present the privacy attacks part, and then I'll give the mic to Igor, who will talk about Opacus. All right, so there are multiple types of privacy attacks, and a privacy attack is when someone can extract information about training data by accessing a machine learning model. So probably the most iconic version of a privacy attack is a full-blown reconstruction attack. So let's say that you have access to an NLP model that does text completion. If you start by inputting a sequence to the NLP model, it will provide completion. So there's this famous XKCD example where someone is able to extract a secret meeting for a revolution by accessing a language model. But it's actually a real threat, and it has been shown recently by Carlini et al. That you can start from a trained NLP model and have it generate sentences, and then if you do some clever filtering, you'll be able to reconstruct sentences that were in the training sets. So that's the setup where I think it's the scariest one, because the adversary only needs access to a machine learning model, and they can generate whole samples from the training sets. Then there are other setups where the task is easier for the adversary, such as attribute inference or like image completion. Here, the adversary has access to the trained model, and they also know some partial information about someone, for example, a zip code or a birth date, and they will complete this information by probing the machine learning model. And then the last kind of attacks that I want to talk about are the membership inference attacks. So here the adversary has even more information because the adversary has access to the trained model, and they also know the full data sample. So if it's an image, they actually know the pixels of the image. The only thing that they don't know is whether the image or the data sample was in the training set or not. So this is what I like to call the least significant bits in privacy. So the idea is that if you cannot even figure out this bit of information, probably you won't be able to do any fancier reconstruction. So these various types of attacks can actually serve as a hierarchy. And the way we will use it is to say that, so basically we will probe and test the privacy of machine learning models by using the membership inference attacks. And if the membership inference attack fails, we assume that any of the more advanced attacks will also fail.
So this argument can be made rigorous if
I'm sorry, my mic dropped. Can you hear me? Okay. This argument can be made rigorous. So let's say that we have an algorithm that performs a reconstruction attack. we can give a model to this reconstruction algorithm. It will generate samples, and then from that we can construct a membership inference attack that just says whether this sample belongs in the reconstructed set or not. And this is a valid membership inference attack. And so if the reconstruction attack is any good, then the membership inference will be non-trivial. All right, so there are, I think, two main families of membership inference attacks. The first family is the family of simple and effective attacks, and they are score-based. So the idea is to compute a score on the model and the data points. And there are various types of scores that are like the obvious scores that you would use in machine learning. So the most obvious one is probably the loss. So you compute the loss of your model that your model has on the data point. Another one is the confidence. So that's for a classification model, the confidence is the probability of the most likely class versus the loss would be the log probability of the correct class. So it might not be the most likely. Another one is the gradient norm. So all these scores, basically, if a data sample is in the training set, then you might, it's probable that the loss is low. So if you just use this score, you'll be able to infer some of the training data points. And then there is another family of more advanced attacks, such as the shadow models and their variants, that I'm going to go into a bit more details about. So what are the shadow models? It's a very high level explanation, but the idea is that the adversary, on top of having access to the model and to like candidate data samples, the adversary also has access to a pool of public data that follows the same distribution as the data that was used to train the model. And the adversary will use this public data to simulate training models and to get statistics about what's the typical behavior of a model on training data versus what's the typical model behavior of the model on test data. So the adversary will do n different splits between a training and a test set. And every time it will train a model on the training set and then evaluate on the test set. And this way it will, like the adversary would be able to gather the statistics and conduct a more advanced attack. So the first family of attack is what I call the effortless attacks. And this is very important because when you go to people and you try to convince them that privacy is important, it's better if you can make your case by not doing any efforts. So typically, people when they do machine learning, they will have a training set, a validation set, and they will have a trained model. This is probably lying around somewhere in their code. And from these three elements, you can run the effortless attacks. So you can already deduce like some non-trivial information and do a sort of like post hoc analysis. Then if you want to get more accurate attacks, you'll need to retrain models because you'll need to do the shadow models that I just explained. So this is a bit more involved, but it's also something that's possible with the privacy linter. So what is the privacy linter? It's a simple and modular PyTorch framework that we have open sourced. The GitHub link is at the end of this slide if you want to check it out and try it on your models. And the goal of the privacy linter is to evaluate these privacy attacks. It's called a linter because if the attacks succeed, it will tell you that your models lack privacy. But if the attacks fail, it doesn't mean that your model is private. If you want to have any guarantee that your model is private, you need to do the DPSGD, and that's what Igor will talk about. So the two main objects that are in the privacy linter is one, the attack results object. So once you've run the attack, this object holds the like state of the attack, and from that you can compute metrics such as the accuracy of the attack, the AUC, precision recall, etc., as well as a bunch of utilities, so balancing data, grouping samples to perform grouped attacks, etc. So for the attack, currently we have implementation of the score-based and the shadow models in the library. What's coming soon is an extension to the shadow model variants, so the work of Carlini and Watson. And in the future, we plan to keep up with the state-of-the-art attacks. Okay, so here is a simplified, but I would say typical example of what a membership inference attack looks like. So that's the results object. So let's assume that you have computed your scores on the training and test set. If you plot the distribution, you will see like two different distributions. And the results object allows to compute the maximum accuracy and the maximum accuracy threshold. So that corresponds to the red line that separates between the training and test distribution. So on the left is a like extreme example where the accuracy of the attack is 90%. The distributions are very different. And on the right is a less extreme example where like the two distributions are similar, but they are still somewhat different. So you can get an accuracy that's slightly, or like that's better than 50%. So now, how do we generate such an object in real life? I talked about the effortless setting. So in this effortless setting, you will need a train model, a train loader, and a test loader. And let's assume that you run the loss attack. So you instantiate this attack object, and then you do attack.launch on model, train loader, and test loader. And most likely your test set is smaller than your train set. So the results will be unbalanced in that there is much more elements from the training than elements from the test set. So we have this utility called balance that allows to like rebalance the results in the results object. So this was for the effortless setting, and now there is the most accurate setting where we will train shadow models. So here we need to do three different things. First, we need to set up the split of the data. Then we need to actually train the shadow models. And after the shadow models have been trained, we will launch the actual shadow models attack and get the results object. So first, for the setup, we have this utility called divide data that will split the data between a public set available to the adversary and the private set used to train the model. And will basically split the public set into multiple different, like along multiple different lines. So it will generate a dict of splits to like Boolean that says whether the sample is in the split or not. Then you need to modify the training code. So instead of having the regular training dataset, you will have this like mask dataset utility that we provide that basically selects only the samples for which the corresponding mask is equal to 1. So this means that you need to modify this training set and then launch training on the various splits. And once these trainings are done, you can load all these models, load the masks and the data loader, and create this attack object. And then when you launch this attack object, you will be able to gather the results. Okay, so that's all for me, and I'll give the mic to Igor.
Right, thanks, Alex. I think I'll take over the screen from you, if you don't mind.
Yep.
Cool. So can anyone see my screen?
Yep.
Cool. So in this part of the talk, we'll talk about one of the common ways to counter the attacks that Alex just described, and the mathematical rigorous way to do this is the differential privacy and the PhD as a way to train differential private ML models. And in this talk, we'll start with a recap of how the algorithm works and what are the steps that makes different from normal SGD. Then we'll talk about our tool Opacus, and we'll just take a look at the basic interface and some basic facts about how it works. Then we'll take a deeper dive into Opacus's code and look into how it works under the hood in one specific aspect, which is principal gradient computation. And then at the end, we'll share a miscellaneous collection of various tips and tricks on how to successfully train a model with the PhD and what's important when you actually start doing it in practice. So first of all, what is the PhD? here on the top right, we have our normal stochastic gradient descent, and just to get comfortable with the notation, let's go over it. So we have our data sets, in this case, just numbers range n. We shuffle this data sets. We split it in chunks, which we'll call batches, and then we iterate over these batches. And for each batch, we go over each sample in a batch. We compute the loss. That's L over here. We compute the loss. We then compute the gradients of that loss with respect to all the weights. And then we take an average of this gradients across the batch and call it model updates and update the model with that gradient. So kind of the steps are clear, and there are four things that we need to change to make it differentially private. First is obviously we need to add noise, and what we do here is the first bit of blue text over here is that for every gradient that we use to update the model, we add calibrated Gaussian noise so that we satisfy certain privacy parameters. In order for that to be successful, we need to be sure how much noise we're adding compared to the individual gradients. And also we need to actually make sure that all of the gradients affecting the overall batch gradients on a similar scale, because outliers will have, if you have outliers in your batch, they will suffer worse privacy leakage, and we want to avoid that. We want to provide the same guarantees for all samples in our dataset. So that's why we do what's called gradient clipping, where we take a gradient and we scale it down so that its L2 norm is below the thresholds that we've set. Step number 3 is somewhat technical. It's in theory, it's kind of it's very PyTorch and TensorFlow specific, and I think that's not really applicable to frameworks like JAX, where you just get principal gradients out of the box. Unlike that, PyTorch and TensorFlow don't let clients access intermediate steps where they compute pro-sample gradients. They only give access to the overall batch gradient. So they optimize the gradient computing process, but as a result, as a client, you cannot get access to the intermediate step. So in order to do that, and in order to do the gradient clipping, we in Opacus had to re-implement gradient computation and make it so that we can have access to the individual gradients of every sample. And the last one, the last step that we need to do to change classic SGD is post-on sampling. Unlike normal batch process where we shuffle the dataset and split it into batches, we slightly changed the sampling process. And now we, for every optimization step, for every batch, we go over the entire dataset. And for every data sample in the dataset, we toss a biased coin and with a certain probability, include that given dataset into a batch, which on average, on the face of it, is not that different from the classical way of doing it, but we'll go over some slight differences in detail. And post-on sampling is mostly there to make the math work neatly and make accounting easier. So this is a visual representation of the PHGD. Just to recap what is going on and what's important. We have 4 data samples in a batch over here on the left. And here what's depicted is backward pass, where we have our gradients gradients of the loss, which are back propagated to the layers. And thickness of an arrow here represents the norm of the gradients. And as you can see, let's say that our last 4th gradient is larger than the others. So when we start computing gradients of the loss with respect to layer parameters, what we do is first we do gradient clipping so that all of them are on a similar scale. Then we aggregate them. Basically, we compute the mean of these gradients, and then we add noise to these gradients, and then using this noise gradients, we update the weights of the model. And here's how it looks in Opacus. So what you need to do to enable this for your training pipeline is quite simple. So let's say we have code on the right here. And let's say that we have a training pipeline where we've already initialized model optimizer and data loader. What we need to do next is initialize Opacus object called privacy engine, which is the main entry point for Opacus API, and then call a method called make private. Make private gets 3 training objects as an input: model optimizer, data loader, and configurations for the privacy parameters. So that would be noise multiplier, how much noise to add, and therefore how private the results of the training is, and max grad norm, which describes how aggressive the clipping is. What we get as a result from make privates is the custom versions of the same training objects: model optimizer, data loader, which you can then use as you would normally do in PyTorch training. And as a result, you'll get DPHD training. So what we do is we assign extra responsibilities to these objects, wrap them in a new privacy-aware classes, and return this privacy-aware objects from make private. So this is a visual representation of what happens within inside the make private method. We have an N module that's normal PyTorch module as an input. We pass it to make private, and make private returns the wrapper, which acts exactly like normal PyTorch module, but also compute pro-sample gradients. In a similar fashion, we get for the optimizer, we get normal vanilla optimizer, and we return the wrapper, which again acts in exactly the same way as normal optimizer, but also adds gradient clipping and noising to the process. And lastly, we have data loader, which the only change we make is we enable Poisson sampling as a default. The next step is privacy accounting. We want to calculate how much privacy we spent and what's the epsilon for our given training is, given all of the settings of our training pipeline. And for that, we have a method called get privacy spent, which at the end of training you can call to get epsilon. And what's interesting is we've seen recently some interesting papers on different accounting methods to compute epsilon based on privacy parameters. And we provide flexibility for people to experiment with different privacy accountants and even implement their own ones. So if, for example, there's been a very interesting paper on numerical differential privacy. We haven't yet implemented that, but if someone wants to do that and want to experiment with that particular accountant, we provide an interface for clients to implement their own accountants and plug them into Opacus training so that they can benefit from Opacus interface while experimenting with their own code for accounting. Next, let's talk about how we compute pro-sample gradients and what it takes to add more layers to Opacus. So let's take a simple example of linear layer, and also let's drop bias. So let's say that we have linear layer without bias. And if we look closely at how the loss of the gradient of the loss with respect to each individual weight of that linear layer looks like, we see that there are only 2 scalar components that participate in the gradients for each individual weight. And those are one component of the input's activation vector and one component of the backpropagated vector of gradients that are being backpropagated from the loss. And this is the actual piece of code from Opacus that implements pro-sample gradients for linear layer. We use the mechanism called hooks in PyTorch, which gives you quite deep access to the inside of PyTorch. And it basically hooks your methods to the backward pass, where your method gets access to the layer itself, the activations, which is the vector from the forward pass, and backprops, which is backpropagated gradients. And if we look once again at the equation, what we actually need to do is do a batched matrix multiplication to get per sample gradients. So that's pretty much it. Here we actually use Einstein, which is a generalized way of doing matrix multiplications, which also lets us handle gracefully handle middle dimensions, which are not which supported by normal linear layer, and Einstein lets us gracefully handle them and not get in the way of the actual matrix multiplication. So the interesting part about this is because we need to implement per sample gradients for each layer that we can encounter in the model, it works by open list of layers that we explicitly support. So if we encounter a model that we haven't seen yet, we don't know how to compute per sample gradients for it, and therefore Opacus cannot work with it. What we provide for this is if anyone wants to use a custom layer that's they've either implemented themselves or have otherwise or for other reason not supported by us out of the box, we provide a way for you to write your own per sample gradients methods and attach it to Opacus. We use this decorator register grad sampler, which says that which tells Opacus that it needs to use this function to compute per sample gradients for this layer that is passed to that decorator. And it's kind of handy if you can figure out the math of your layer and want to experiment how the DPHD affects the model if you use this layer. And now we get to the last part of the presentation, where we share various unconnected tips and tricks on what we've learned from actually training models with DPHD and what's important. And let's start with Poisson sampling. As I've mentioned before, on the face of it, it looks like it doesn't really make that much of a difference. Kind of you, instead of shuffling, you do independent sampling every time, but how different could it be? Well, it's different in two ways. Let's say that we have our batch size that we want to simulate is 16, and if we wouldn't be using Poisson sampling, our batch size would be of size 16. And we set our sampling rate so that on average we have batch size 16. And what we have here on the graph is the actual distribution of actual batch sizes that you get if you set sample rates for the average batch size of 16. So you can see that the peak is obviously at 16, but there are plenty of batches that are larger and smaller than 16. It creates two problems. One is large batches. Pretty much every single batch that is larger than 16 is a potentially out of memory error, because the way we often set batch size is to maximize the utilization of our GPU, and so that's we set the batch size so that it fits. We know that it fits into GPU, but also utilizes memory to the max. Well, in this case, we cannot really do that, because if we can only fit the batch size of 16 on a GPU, pretty much half of our batches that are Poisson sampled would be larger than that. And we face a choice between either, well, we actually don't have a choice, but deal with underutilization of our GPU by setting batch sizes lower than we would have otherwise. And the second problem comes from the other end of the spectrum, and that's batch size of 0, which is with reasonably large batch sizes, it wouldn't be too common, but it's still possible. And many pipelines are not really expecting to see tensor with the first dimension of 0, which could often lead to unexpected errors. The second problem, and it's somewhat related, is resource consumption. It's natural that computing more gradients, computing per-sample gradients, storing per-sample gradients takes both time and memory. And in this paper, group of researchers analyzed, they've trained GPT-2 with various DPHD frameworks, and they analyzed the impacts of that on the memory and throughput. And the graphs demonstrate that blue is non-private, red is Opacus. And you can see that we have almost threefold reduction in the maximum batch size and twofold reduction in throughput in terms of examples per second, which means that training with the DPHD is expensive from a memory standpoint at the very least, and from the throughput standpoint as well. And if you put that together, on average, we've observed that you face 5x to 10x reduction in the training speed. One way of addressing at least memory concerns, and it works for both Poisson batch memory concerns and just plain through memory problems from the DPHD, is batch memory manager. So the idea is to separate the concept of physical and logical batches and say that, sure, we can have Poisson batches of any size, but the actual physical batches that we'll show to the model and will process in a loop will be smaller. And what we do is we put an extra layer in between Poisson sampling and the training, and pack it as a context manager called batch memory manager, which takes the sample results from the Poisson sampler and then split them into chunks of a fixed size, where it keeps track of which chunk is the virtual one and which one corresponds to the end of an actual batch where we need to do actual optimization step. And just to demonstrate how it works, here's the piece of code that shows how to apply it. Everything that is within the context manager is normal training loop that doesn't require any changes. And you wrap it with the batch memory manager, context manager. You pass data loader, max physical batch size, and optimizer, and you get new data loader that you just use within the context manager. And the reason we need optimizer here is that because batch memory manager signals to the optimizer which batch being processed, whether it's a virtual one or a physical one or an actual logical one where we need to do optimization step. Another thing to address privacy issues is the parallelization and distributed processing. It's pretty much impossible to imagine modern ML training without on a single GPU. So what we need to support in Opacus is some sort of distributed processing, which we do by supporting DDP. And just a quick guide on how to do it. On the left here, we have a normal PyTorch flow of applying DDP. That's you initialize DDP backends, you wrap your model with a corresponding wrapper. You then initialize data loaders while keeping in mind how many GPUs you have. So for example, if you know that you want your logical batch to be 68 and you have 8 GPUs, you know that each GPU should receive a data loader with batch size of 8. And then you use local rank as device ID. With Opacus, it's somewhat similar with a few slight changes. So first, you initialize DDP backends as usual. You then wrap model with DP-DDP, which is part of Opacus distributed package, and there are no changes here but the name. The important change comes at the third step, where you don't need to keep in mind how many GPUs you have. You initialize data loader as if you're training on a single GPU without any mention of the distributed sampling or changes to the batch size. And you pass that to the privacy engine of Opacus. And then, as normal, you would use local rank as device ID. The interesting bits on the hyperparameters is pretty much half a year ago, 6 to 8 months ago, we all believed that training large models with DP is near impossible because in theory, and that is true, that is the case, that the amount of noise you add scales with the number of parameters. And the more, therefore, the larger model is, the more noise you effectively add to the model, which we thought that put a limit on how large the model could be that you can effectively apply the PhD to it. However, in the last few months, there were a few impressive papers from groups at Google and Microsoft Research, which demonstrated that using some tricks and techniques, you can actually train very large models on a scale of GPT-2 and large birds to effectively to be actually quite decent in accuracy metrics. So we're talking about the models of hundreds of millions of parameters, and they're not quite there for the non-private baseline, but they are decently close and within they are definitely better than non-private and much smaller versions of the models that apply to the same tasks. And notably, there are two common features that are shared between these papers. And we think that they are actually very important for training DPHD efficiently and effectively. First is huge batches. They're ranging a lot from 2 to the power of 10 to the power of 16, but it's still much larger batch size than you would expect on the non-private training. So that's one thing to keep in mind, that if you want to add a lot of noise, just make batch larger, and that will help with reducing noise to signal ratio. Well, yeah, reducing noise to signal ratio. And the second one is doing Adam optimizer, which is surprisingly resilient to noise. And even with really large amount of noise, it managed to train something. It's actually a very interesting topic as to why exactly this is happening, but empirically, this is clear that this is the key to many successful trainings and makes a lot of difference when you train the PhD models. And lastly, to conclude, I just want to share the resources that we have as Opacus team. We have a website where we have tutorials on both DP training and how to use Opacus. We are open source frameworks, so we welcome every contribution, be it pull requests with a new feature or feature requests or bug reports on our issue boards. And also we have a technical paper you can cite if you're using Opacus in your research. And on that, thank you very much for your attention. I will stop share, but I'm open to share my screen back if there are any questions.
Sure. Thank you very much for the very nice and very interesting presentation on these softwares. I think, Georgie, we can stop the live streaming now.